So hello, this is a presentation for our research paper titled Sub-Path Accelerating Image Generation with Sub-Path Linear Approximation Model. And so let's begin with a brief look at these preliminaries. We start by recognizing the effectiveness of consistency models. Start from training a typical denoise with noise prediction objective. We found that consistency models leverage the approximation strategy, which assumes a very large generator as f sub theta to minimize the prediction errors, and it could recover the original x sub t from x sub t minus k. Such an assumption results in an approximate learning objective, which helps the model to escape from the case that the term alpha t times x sub 0 should be close to 0. Also, thanks to this approximation, the prediction error in consistency models can be confined by the cumulative errors as depicted here. And still, the learning strategy remains some problems. As shown in this figure, each optimization of the points on the PFODE trajectories should rely on the optimization for former time steps. So if the maximal time step t gets larger, one potential problem is that the increasing number of the approximations may amplify the overall prediction error, and the convergence for the model could be dilated by the stepwise convergence for its time steps. And so in this paper, we address this issue by extending the original cumulative errors with a sparser sampling and an increased skipping step size k. The modified formulas are presented as below. Additionally, the learning objective has changed as well. We observe that the risk of the new learning objective now is primarily associated with the first term, which focuses on the diffusing effect during the transition from x sub t minus k to x sub t. We define this term as distance delta. The middle term is optimized by the learning at x sub t minus k, which I have assumed to be well learned. For the first term, as k approaches t, the x sub t minus k term is going to be multiplied to 0, which makes the distance delta intractable to estimate and is hard to be optimized. So to overcome this challenging learning of distance delta, we propose a new accelerating approach which we call as PLUM for short. Here, we redefine the optimized error at each time step as a learning objective for the subpath determined by two sample points. It's evident the distance delta can occupy a significant portion of the optimization process, as shown in this figure. To prevent an uncontrollable increase in this error, we introduce an additional approximate ODE in this paper to help the learning. The additional subpath linear ODE can be defined as follows. It represents a straightforward linear interpolation between x sub t and the scared x sub t minus k due to the drift process. We have constructed this ODE because we have discovered that an important property for this ODE, as shown here. By introducing this extended point into the original learning equation and leverage the approximate error estimation, which can be expressed as the loss of SL ODE. And finally, we can deduce the learning objective for our SPLUM as below. Compared to the original scenario, the most notable change is the introduction of a gamma coefficient in the approximation learning. Thanks to this coefficient, we now can estimate the distance delta continuously and progressively during the optimization in our training. This capability also allows the model to manage a much more larger skipping step size k, thereby reducing the overall cumulative error and facilitating faster convergence. For our experiments, the results have shown that we not only achieve optimal FIDs, but compared to LCM, which directly adapts consistency models into stable diffusion models, as PLUM exhibits more faster convergence when k is set to a much larger number. We also directly estimate the approximate error for each time step, and the results serve as evidence of the effectiveness of our method. For the improved generation, the tested results suggest that the improved FIDs are likely due to the enhancement in details such as image clarity or reflections by a leg side. We also compare our SPLUM with open-source LCM, and the performance gap is quite evident. So that's all for this presentation, and thank you for listening.